Okay, my friends, in this video, we're going to talk about what happens when real gases don't act like the ideal gas law would predict, okay? So we're going to be dealing with things like pressure, IMF attraction, volume and mass, and temperature, and kind of how it works, all right? So remember that real gases, they do act ideally in our normal environment. So I want to make sure we're clear about that. So under normal conditions, real gases and ideal gases are great, okay? We can use all the equations that we did in this unit to solve for how real gases work by using these ideal gas laws and that kind of stuff, okay? But what happens if we push past normal, all right? And that's what's kind of fun about honors chem is we can go past typical or normal and talk about it, all right? So what we want to first talk about is this concept of compression factor, all right? If we look at the ideal gas law equation and we set both sides over each other and divided them, they should equal 1. Which means in any scenario, if you were an ideal gas, your pressure times your volume divided by your moles and your temperature and the ideal gas constant should always equal 1. So real gases should always follow this perfect graphical line of 1. Okay? If our y-axis is that, it should always be a 1. However, we see that real gases under really high pressure, 300 atmospheres, 600 atmospheres, 900 atmospheres, 300 times normal atmospheric pressure, we see these dips and these spikes. So why does that happen? Here we go. Let's find out. Okay. First of all, IMF attraction. Okay. If you remember, we set up some parameters that ideal gases have 0 IMF. Well, real gases have very, very, very little IMF, which means that if the ideal gas law would predict a pressure of this, okay, a real gas would have slightly less pressure because of the IMF attraction, okay? So things with really strong IMF attraction are going to shift this scenario because the pressure is going to be less than what the ideal gas law would predict, okay? Right? Ideal gas law would predict this number, whatever this number is, the real gas would be slightly less, okay? So under normal conditions, this little gap here is so small, it's mathematically negligible. But under high pressure conditions or very cold temperatures, it's not, okay? So when will this have the biggest effect? Well, the stronger the IMF, right? The stronger the attractive force, the bigger this is going to have a role to play as we go through it. So strong IMF gases are going to have less ideal than real. Number 2, particle volume. Again, we said that ideal gases, that the individual atom space, we ignored, okay? It'd be kind of like saying, I'm going to take you and 4 of your friends, I'm going to drop you into the boundary waters. I'm going to say, okay, I want you to figure out how much volume is out here. But make sure that you subtract away your volume because you're now taking up that space. Well, that'd be ridiculous, right? Because there's 4 people in the entire boundary waters canoe area, which is thousands upon thousands of acres of land. You taking up, a 2 foot by 2 foot square does not change the overall volume of that space mathematically, right? Yes, it does a little, but mathematically not really. You wouldn't factor out your volume because you're there, okay? Same thing for particles of an atom. Normally we ignore them, all right? But real gases do have a very, 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 very small amount of volume. So the exact opposite happens here. So if this circle represents volume, the ideal gas law would predict it to be this size, the blue dotted line. Real gases would be a little bit bigger. So if we go back here again, volume is actually, for real gases, is actually a little bit bigger than what the ideal gas law predicts. Well, pressure's a little bit less, volume's a little bit bigger, so normally they kind of cancel each other out under normal conditions, okay? So when we get non-normal conditions, extreme conditions, they start to be out of whack. All right. So when will this have the biggest effect? Well, the bigger the molecule, right? So the bigger each atom is, or the bigger the molecule is, it's going to have a bigger effect. Big things have a bigger effect than little things do. All right. So now let's talk about our scenarios in which we get deviation or a variation off the ideal gas law. Scenario number 1, high pressure. Okay. So as we build pressure, we get more and more pressure. Real gases act less ideally, okay? Think about this. If ideal gases existed and there was no real gases, you could never make a liquid. Kind of weird, but you couldn't. Because If we pressurize gas enough and pressurize gas enough, what happens is eventually they get so close to each other that the IMF starts to attach to each other and we create liquids, right? Because that's what liquid is. It's the bonding of IMF to each other, right? So under high pressure, we should get liquefying things. It actually happens in propane tanks. When you pressurize propane tanks, you actually have liquid propane in those tanks. You can hear it sloshing around, okay? But as soon as you release the pressure to go to your grill or to your camper or some sort of thing, it goes back to a gas because the pressure decreases, okay? So let's talk about what's going on. As you build pressure, the IMF attraction, okay, is going to attract things and make them smaller, right? So the stronger your IMF attraction, as pressure starts to go up, we see a dip because the volume gets smaller than what the ideal gas law would predict. So the V here is less than this prediction. So we see it going to be less than 1 because we're making the numerator less than 1 here. So over the nRT, this whole overall will be less than 1. That's how we see the dip at first. But as pressure continues to build, eventually those particles, the actual individual molecules, start to hit each other and they push back and they create more volume. So eventually they level off and actually go the other direction. So the volume of the particle starts to play a big role at extremely high temperatures. So at first the attraction pulls it in, and then later on it actually pushes back as the volume of each individual molecule plays a role. Okay? So we have a take home for this. Under high pressure conditions, anytime you have stronger IMF or bigger atoms, the real gas is not going to act as ideally. Okay? So that's what we're talking about. So gases that have strong IMF and are big won't act as ideal. But it doesn't matter at all unless you're under high pressure as one of your scenarios. Okay? Because we're just putting so close to each other. Scenario 2, low temperature. At low temperatures, it's the same effect. It's just the fact that instead of putting them really close to each other, we make them move really, really slow. Okay? As you cool things down, they have less kinetic energy and they're moving slow, which means, once again, their IMF is going to pull things in tighter, right? It's going to attract them more, okay? And it also means that the heavier the atom, the bigger those atoms are, they're already moving slower, right? So at any given temperature, things that are heavy move slower than things that are light because they have to maintain energy. So again, we deal with low temperatures when things are moving really slow. They just don't have the energy to just fly by those intermolecular forces that are holding them together, okay? So as a result, they cool down, and eventually they would turn to a liquid if they're a real gas. Ideal gases would never liquefy, okay? So under this scenario of low temperatures, because they're moving so slow, heavy atoms are going to be a bigger role because they're already moving slower. And gases with stronger IMF are going to be a bigger role because they have stronger attraction forces. Okay, so again, we see that dip and then the spike. This graphic's kind of nice. We see 1,000 kelvins, 500 kelvins, and 200 kelvins. So you notice that the hottest gas, okay, is the one that stays closest to this ideal line the longest. Okay, it takes 50 or 60 atmospheres or 50 or 60 times atmospheric pressure, which is crazy high pressure. We don't ever get that. Most containers would explode before that happens, before they even varies off of that line. Okay, cold gases vary more, hot gases vary less. Okay, so here's our take home: anytime real gases move slower, they act less like an ideal gas. Okay, so let's talk about 3 different gases and 3 things, and of these, let's answer some questions. Okay, so question number 1. Okay. Why does helium follow the ideal path best? Okay, so helium is yellow here. We see that it follows the path the best. Well, let's talk about its IMF. Helium is a noble gas. It's not a diatomic. Its IMF is the weakest of all of our gases. Okay, so it has extremely weak IMF. It can barely London dispersion force. It can't dipole-dipole. It definitely can't hydrogen bond. Okay, so extremely weak IMF. And helium is tiny. It is the smallest of all of our gases. Hydrogen is actually bigger than it because it's a diatomic, okay? So helium is the smallest atom with the least amount of attractive force. That's best case for ideal, okay? Why does ammonia dip below 1? Well, ammonia, remember, is a polar molecule, pyramid shaped. It's fairly big in terms of gas size, strong IMF, Okay, so it's big with a strong IMF. So as it starts to get more pressure, that IMF is going to attract things down tighter, which is going to make it dip. Okay, and then why does nitrogen spike? Actually, this question can say why do all three of them spike, because it's all for the same reason. As the pressure builds more and more and more, eventually the size of the individual atoms get in the way, and they actually create less space, so that space pushes back. Okay, so the more pressure we get, all gases are going to spike. Nitrogen tends to do it more than the other one too, but they all are going to do that because the volume of the individual molecules. Okay. All right. So take homes from this. When does the ideal gas law become less valid? So when would you not want to use the ideal gas law mathematically to solve for things? Well, if you're high pressure, extremely high pressure conditions, or extremely low temperature conditions. Okay. We're talking industrial things that are above your normal day-to-day lives. We're talking temperatures below the coldest you've ever seen in Minnesota. Okay, so nothing in our day-to-day moving around, propane tanks, acetylene torches, nothing like that is going to affect this. The ideal gas law would hold fine for that. Okay, and then what type of gases act less ideally? Well, the stronger the IMF. So things that are polar, can hydrogen bond, they're going to be ones that act less ideally. And the bigger they are or the heavier they are, it's going to be the way it is. Okay? So that's kind of take home. We'll do a little bit more review of this in class for sure, too. All right. So, need some more information? There's a great crash course chemistry that explains this. It's a lot longer than my video, but they actually go into the math behind it. So, if you're interested in what kind of correction factors you have to put in, if you needed to, they walk through what those correction factors would be, and you'll see how complex the math kind of gets. You might be interested in it, especially if you're a mathematical kind of person. And they also give a little history behind it, or in terms of like how we figured it out and where it all came from. Okay, so if that interests you, this is not a sign by no means, but if it interests you, go check it out. All right, my friends, that's it for this one. Thank you.